Hey everyone, Katrina here, and today we're going to talk about algebraic versus geometric multiplicity of eigenvalues. Be sure to subscribe for more videos like this. Okay, so I've posted a few videos already which discuss algebraic and geometric multiplicity of eigenvalues in great detail. So this video is a little bit different because we're going to go through another example where we have an algebraic multiplicity of 2 and a geometric multiplicity also of 2. So we're going to show the step-by-step way how to use different algebraic manipulation, finding eigenvalues and eigenvectors to get to this result. However, I'm first going to go over the definitions for algebraic and geometric multiplicity for those of you who are just joining me for the first time today. If you've already seen that, feel free to skip to the example. I have it pinned down there in the description, so I might see you then. Okay, so for those of you who this is your first time watching about this, we're just going to go over what is algebraic multiplicity of an eigenvalue. So it is the number of times the eigenvalue appears as the root of the characteristic equation or polynomial. So the characteristic equation is defined here as the determinant of a minus lambda I. So let's break down each of these parts. So A is a matrix, our square matrix here. Lambda is our eigenvalue, which is a scalar value. And then I is our identity matrix. So identity matrix is any matrix that has ones down the center and then zeros everywhere else. So the trick here is that the size or the dimensions of I have to match the dimension of A. So as a quick example here, I just wanted to draw your attention to this. So if we were to already be given a factored form of the characteristic equation, let's determine the algebraic multiplicity. So we can see that this first term has a multiplicity of 2. So that means that, that means that our lambda 1 equals to lambda 2, which equals to 2. And then our lambda 3 here equals to negative 1. So that means this first part over here has an algebraic multiplicity of 2, and this part over here has an algebraic multiplicity of 1, because 2 appears twice as the root, whereas negative 1 only appears once as the root. We're going to move on now and discuss the definition for geometric multiplicity. So geometric multiplicity tells us how many independent eigenvectors correspond to each eigenvalue. In essence, it is the dimension of the eigenspace associated with that eigenvalue. So if we were to look at, okay, how do we actually find this? First of all, we need to determine the eigenvectors. So the equation for eigenvectors is AV equals to lambda V. So if we dive into this equation, let's annotate it. So we already know that A is our matrix. We know that lambda is our eigenvalue. I'm just going to use this notation with our kind of cursive epsilon E for eigen. And then this V over here is, I'm sure you can guess, is our eigenvector. Okay, so typically we will rearrange this equation when we solve for it. So we would bring it all over to one side first. So AV minus lambda V equals to 0. And just for those of you who are not aware, this hat on top of our vector V just indicates that it is a vector. And then from here, we can factor out a V such that we have A minus lambda multiplied by vector V, and we set that equal to 0. So when we're solving for eigenvectors, we solve for an eigenvector that corresponds to a particular eigenvalue. So we might say that for lambda 1, for eigenvalue number 1, we're looking for our eigenvector number 1. So we find eigenvalues, we find eigenvectors associated with particular eigenvalues. So now we're going to jump into our example. So in my previous videos, I've shown different cases where we might have an algebraic multiplicity that's more than 1 and it's greater than the geometric multiplicity. Other examples I've shown algebraic and geometric the same and equal to 1. Today it's going to be a new case where we're going to look at algebraic multiplicity greater than 1 and geometric multiplicity greater than 1. So for our example, we have matrix A, and matrix A equals to 2, 0, 0, 2. So I always like to take a moment and kind of analyze what I'm dealing with. So first of all, we can see that matrix A is square. Second of all, we can see that the dimensions is 2 by 2, so 2 rows and 2 columns. And the other third thing that I see here, which is quite interesting for me, is that A is a symmetric matrix. And symmetric matrices have very special properties in linear algebra. They have lots of special implications. So knowing that this is symmetric is important because it's actually going to indicate to us that we will have an algebraic multiplicity equal to a geometric one. But we're going to go through all the steps anyways so we can find it. So step 1 is we wanted to find the algebraic multiplicity. We need to find the eigenvalues of our matrix because we need to determine how many times each of these eigenvalues is a root of our characteristic polynomial. So if we go back and recall our characteristic polynomial, it's the determinant of a minus lambda I equals to 0. So for those of you who need a little bit of a refresher on how to find determinants, say we have some matrix, let's say E for example, and it equals to elements A, B, C, D. For a 2 by 2 matrix, the determinant of matrix E equals to AD minus BC, and this will be a scalar value. So now that we know it, let's go ahead and just simply input our values into this equation. So we're going to start off with matrix A. So we've got 2, 0, 0, 2 minus lambda times our identity matrix. And recall again that our identity matrix must be the same size as our matrix A. So we're going to use scalar multiplication and matrix subtraction here to get this into one term. So we're looking for the determinant of, let's see if we can write this all out in one step, 2 minus lambda, 0, 0, and 2 minus lambda. Okay, so now we're going to go ahead and use our little matrix formula that we learned to write over here. So knowing that, let's see what we get. So we've got that our determinant equals to, we have our first diagonal multiplied by each other. So we've got 2 minus lambda times 2 minus lambda, and then minus our second diagonal. So we've got 0 times 0, and we're setting this all equal to 0. So as a result, we end up with 2 minus lambda times 2 minus lambda equals to 0. And this is wonderful. It's already factored for us, so it's very happy. Less work for us to do. So here we can simply see, in order to solve for lambda, we just set each of these terms equal to 0. So we get that lambda 1 equals to 2 and lambda 2 equals to 2. Okay, so what is this telling us? So that means lambda 1 equals to lambda 2, which equals to 2. So that means 2 appears twice as the root, right? As the root of our characteristic equation. And because it appears twice, well, that tells us that therefore the algebraic multiplicity is equal to 2, because that eigenvalue appears twice in our characteristic polynomial. Sorry. So now we have to move on to step 2 of our example, which is we want to find the geometric multiplicity. And in order to find that, we need to find the eigenvectors. So we're going to follow our a minus lambda times v equal to 0 equation that we derived above. So we're going to write out our eigenvector v as v11 and v21. So we can just see its elements, which is useful for our matrix multiplication. The other thing to note here is that we're finding the eigenvector associated with our particular eigenvalue. So we're going to say that we're looking for v1 in particular over here. So let's go ahead and plug our numbers into this over here. So we've got our matrix A, which is 2 minus lambda, 0, 0, and then 2 minus lambda, and then we're multiplying that by our v11, v21, and setting that all equal to 0. So when we perform matrix multiplication, it's very important that we have the right dimensions, or else it cannot be performed. So here we can see that the number of columns has to equal to the number of rows in order for matrix multiplication to be performed. So here we can see that that condition is indeed satisfied, so that means we can move on with our matrix multiplication. So before we even get to the matrix multiplication, let's simplify this. So let's plug in our value for lambda. So we found that lambda 1 equals to lambda 2, which equals to 2. So we want to plug in lambda equals to 2 into our equation above. So what happens when we do that? This is actually quite curious. We get that 2 minus 2, 0, 0, 2 minus 2, multiplied by v11, v21, set that all to 0. Okay, so what's happening? We end up with 0, 0, 0, 0, multiplied by v11, v21 equals to 0. And okay, so let's perform our matrix multiplication. We get 0 v11 plus 0 v21 equals to 0. And then we also get 0 v11 plus 0 v21 equals to 0. Okay, so what does that tell us over there? Well, this is actually a pretty interesting case. What this tells us is that our equation is satisfied for, oh my goodness, big climax here. So the equation is satisfied for any value of v11 and v21. So any value makes this possible. This satisfies the equation. So as consequence, we can write out the linear space. As consequence, the eigenspace of lambda 1 is a linear space that contains all vectors v1 of the following form. So because this is satisfied like this, we can write our v1, so our eigenvector, as our v11 multiplied by 1, 0 plus v21 multiplied by 0, 1, because we said that it's satisfied for any value of v1 and any value of v2. So essentially we're writing out its components, so we can see that this first part has a non-zero value for the, you can think of that as like the x component, this is the x component, and then a 0 value for the y component, and the second one has a 0 value for the x component and a non-zero value for the y component. So our eigenspace essentially is this linear combination of these two independent eigenvectors. So a couple of conclusions we can draw here. We can see that the eigenspace of lambda 1 is generated by two linearly independent eigenvectors. Okay, so I'll write that out. So we've got the eigenspace for our first eigenvalue. We're saying lambda 1 is generated by two independent, so linearly independent eigenvectors. So these two linearly independent eigenvectors we can see are 1, 0, and 0, 1. So these two vectors are orthogonal to each other. They are linearly independent. So that means that we have two independent eigenvectors associated to our eigenvalue. And we also see that our eigenspace is dimension of 2. So what does that tell us in terms of the geometric multiplicity? So that tells us that the geometric multiplicity is 2. And again, why? Because we have two independent eigenvectors associated with that eigenvalue, and the dimension of our eigenspace equals to 2. So these are both reasons why our geometric multiplicity is 2. So for this example, let's kind of analyze everything that we have. So we said that our algebraic multiplicity equals to 2, and our geometric multiplicity equals to 2. So algebraic multiplicity, we'll just zoom in here, is always going to be greater or equal to geometric multiplicity. That's just a fact of mathematics for you. However, if algebraic multiplicity is actually straight up equal, do that in green here, if it's equal to geometric multiplicity, well, what does that mean? That means that our matrix is diagonalizable, which is exactly what we have in this case over here. So we can see that they are equal, meaning our matrix is diagonalizable, which is awesome. So this example was a bit unique because I showed you an algebraic multiplicity that was above 1 and also a corresponding geometric multiplicity that was also above 1, and they were equal, meaning that we have a case where our matrix is diagonalizable. So if you want to see other examples with other variations of algebraic and geometric multiplicity for eigenvalues, be sure to check out my other videos. Also, if you would like more background on eigenvalues and eigenvectors, matrix determinants, linear algebra in general, be sure to check out the linear algebra playlist because I have videos that go into each of these topics in more granular detail. This topic today really requires you to understand eigenvalues, eigenvectors, matrix determinants, identity matrices, matrix operations such as multiplication, addition, and scalar multiplication. So it's very all-encompassing. So if you're able to solve these problems, that means you have a very good and deep understanding of linear algebra. So congrats to you, and I hope this video was helpful. Please drop a like and definitely comment any questions you have, and please subscribe for more math videos. I really look forward to seeing you next time.